The objective of this paper is to create an online motion planner that moves multiple robots with different sensor configurations towards a goal. The planner should find optimal control values, evaluate uncertainty, and find global solutions. First, stochastic MPC is implemented to move the robots and enable them to avoid obstacles through chance constraints. Here we show the SMPC running online on a ground robot, evading incoming obstacles. We do the same for a drone. Safety is considered through an estimate of state uncertainty. We use different SLAM algorithms depending on the robot's sensor configuration. The outputs of SLAM are fed through an RNN, which predicts, after training, future state uncertainties. Here we show the data collection process for the ground robot using particle filter SLAM, and now visual inertial SLAM for the drone. Because we have a multi-agent system, we implement a distributed comment filter to update the received uncertainties when the robots are in communication range, which also updates the chance constraints. We visually show how uncertainty is propagated, and the instances where both robots are in communication range. Stochastic MPC alone is not sufficient, however, because of local minima problems, as seen here for the ground robot, which is unable to reach the global goal. This is resolved by using a deep Q-learning agent for high-level path planning, which serves as a more optimized sample of target positions compared to typical tree search methods. We trained the DQN agent on a 2D grid and randomized the obstacles for several maps. Here's the result once the models have been trained. The DQN provides target positions for the SMPC at each time step, moving the robots toward a desired global goal. With the DQN, we can now easily avoid the local minima problem. We also can consider more complex cases and find global solutions using our complete algorithm. The same results are shown, but with the DQN proposed path visible. We call our algorithm Stochastic MPC for autonomous bots in uncertain environments using reinforcement learning, or SABER.